Hey, so we have a question here about using Graham's law. And so this is something that comes up usually in chemistry, and it has to do with the rates that gases will diffuse through a porous barrier. Or they could effuse. Is that the right word? Effuse? I think it is. Maybe I'm wrong on that. But basically, to diffuse is to go through a porous barrier. And the other one, which I think is effuse, is to go through like a very small hole. So they're a little bit different, but I guess it works the same way for either one. So here's the thing. Graham's law, let me read the question first of all. So, two porous containers are filled with hydrogen and neon respectively. Under identical conditions, 2/3 of the hydrogen escapes in 6 hours. How long will it take for half the neon to escape? So let's take a look at what Graham's law says. Graham's law, let me bring it up. Here's the one to focus on. This is where Graham's law is at. And what that says is that the rate that one gas diffuses divided by the rate that the other one diffuses is equal to the rate that the second gas, or the square root of the molar mass of the second gas divided by the molar mass of the first one. We're going to unpack what that means here. So let me just write it down. First of all, for our example, so we have the rate, let's go with the rate of hydrogen, and it's going to be the rate of H2. Now the reason it's H2 for hydrogen is because hydrogen in its natural state, at least on Earth, tends to group with itself. So if you took a bunch of elemental hydrogen, it only has one valence electron. It's going to try to grab another electron from a nearby hydrogen atom. So you put a bunch of elemental hydrogen in a container, it's going to, typically it will make hydrogen 2 gas. And then we're going to divide by the rate of neon gas. And neon is a noble gas. Let me bring up my periodic table here. Not that one, this one. Again, hydrogen is in this first group, so it's going to have one valence electron and it wants to try to get 2, so it's going to double up, try to grab one from the other hydrogen. Neon, on the other hand, is a noble gas, so it has 8 valence electrons already. It doesn't want to interact with other gases, not even itself. So it's going to tend to just stay in its elemental form, which is completely uncombined. So it will just be Ne. That will equal the square root of the molar mass of neon divided by the molar mass of H2. And the reason that this is reversed is because this is an inverse law in this case. So if I go back to the formula, you notice it's rate 1 over rate 2. That's equal to the inverse of that, molar mass 2 over molar mass 1. And that's somewhere where you could get easily caught up, so you got to be careful about those. Alright, so let's start with the molar mass part of this equation, and then we'll go back later on and undig these rates. So the molar mass of, let's start with hydrogen. The molar mass of hydrogen we can get from the periodic table, and you see here that this lists that the atomic mass of hydrogen is 1.008 grams per mole. That's that is going to have to be multiplied by 2. So the molar mass of hydrogen, because it's H2 and not just H, we're going to have to take 2 times 1.008 grams per mole. Alright, so I'm going to calculate that to begin with. So it's 2.016. grams per mole of H2 gas. That is the molar mass of hydrogen 2. The molar mass of neon is actually easier to get. We don't really have to do anything with it since, again, it's a noble gas and it doesn't tend to interact with itself. All we got to do is go to the periodic table, find neon, and you can actually see it ends up being 20.1797 grams per mole. And I'm probably leaving more significant figures on these numbers than I need to. So that's, extending this number out to 6 digits is probably not necessary, but it won't hurt anything in the end, I suppose. So that we don't have to multiply by anything because it's just neon by itself. It doesn't combine with itself, so it's good to go. Now, I'm going to start by working out what this square root is. Well, actually, no, let's skip that step, and I'll do that later. We'll figure out the square root later, but basically it would be this 20 divided by 2 under a square root. We'll get to that. Let's look at what these rates are. So, the rate of diffusion or effusion, whatever we're doing here, is going to be the number of moles that go through. I guess this is diffusion because we're told it's going through a porous container. It's the number of moles that go through the porous barrier per unit time. So, for instance, we're told that the gases are under identical conditions, okay? So what I'm about to do might be obvious to you, but I'm trying to be careful here, so I'm going to show you. If we have hydrogen, we can actually look at the ideal gas law for either one of these gases, okay? And we're told that the conditions are identical. So that means that whether or not we have neon or hydrogen, the pressure, the temperature, and the volume of the container are the same. And of course, R, being the constant number, is always the same. So that means if you just look at this as an equation, P, V, R, and T are all the same numbers for hydrogen or for neon, which means if you were to look for N, which is the number of moles, N is the number of moles, then either way you're going to have the same number of moles of hydrogen as you do neon. And that's because your conditions are identical. The container's the same size, the pressures are the same, and the temperatures are the same. So you have the same number of moles of hydrogen as you do neon. Now we don't know how many moles that is, but as I'll show you, we don't actually need to know. So if we look at the rate of hydrogen, it's the rate for hydrogen is equal to the number of moles of hydrogen. I guess I'll put H2, why not? Number of moles of H2 divided by the time it takes to diffuse. I'll just say that's T. Now, all we know here is that 2/3 of those are diffused. So let's say there's a total of m moles in the container to begin with. Then 2/3 of the m moles will diffuse in 6 hours. So it says 2/3 diffuse in 6 hours. So to begin with, there was m moles in the container. We don't know what m is, but it was some number, and 2/3 of that diffused in 6 hours. So from this, I can get 2/3 m times 1/6, and that will give me 2m over 18, which is m over 9. Alright? Now let's look at the rate for neon. And that's going to be the number of moles of neon that diffuse in a given time. I guess I should be careful here and call this time of hydrogen, time of neon. So the number of moles of the neon that diffuse in however long it takes. And we're told that half of the neon will escape. So it will be 1/2 m. In other words, we know that originally it had m moles of neon, because we saw from the ideal gas law that either way, the number of moles of hydrogen or neon was the same to begin with. And in this case, half of them escaped. However, we're not told what the time is. In fact, we have to find out what that time is. So I'm going to say the time for the neon to escape is an unknown. So this will be equal to m over 2 times 1 over t neon. And that's going to be equal to m over 2 times the time for the neon to escape. Now, from our formula up here, Graham's law, we take the rate of the hydrogen divided by the rate of neon. So I'm just going to take my two answers and divide them. So it's m over 9 divided by m over 2t ne. So that's m over 9 times 2t ne divided by m. And this is why it was important that they both started with the same number of moles. The m's actually cancel out. You can just divide them out, and you'll end up with 2t for neon divided by 9. Now, again, going from Graham's law, that rate of hydrogen over rate of neon, which we know is 2t over 9, will equal the square root that we already previously, well, we have most of the information for that. So we can say that 2t of neon over 9 is equal to the square root. It will be the molar mass of neon, which is 20.1797, divided by the molar mass of hydrogen, which is 2.016. So let's go ahead solve for the time. That will equal 9 over 2 times this big square root here. And I'm going to put this in a calculator. So it will be 9 over 2 times square root with a fraction, and then 20.1797 over 2.016. The answer is 14.23 about. And that will actually be in hours, because we know it's in hours because the original time we used was 6 hours. So we stuck with the units of hours. Hours will be the unit that comes out. And I'm going to round that off to just about 14.2 hours, because the answers we were given weren't super, precise. 2/3 and 1/2 was about 0.6, which is only one significant figure. So honestly, even doing 3 is probably more than is needed. So 14.2 hours for the neon gas to diffuse. And just as a check to make sure this kind of makes sense, the hydrogen actually diffused in 6 hours. So this is taking longer to diffuse for the neon. But that makes sense because the neon, if we look at the periodic table, neon is actually a bigger gas. Like the molecules, or the atoms of neon are bigger than they are for hydrogen. So it would be somewhat harder for neon to fit through a porous material than it would be for, let me see, it's this one. It would be harder for neon to fit through a porous material than it would be for the smaller hydrogen. So it makes sense that it would actually take longer. So if you have any questions about that, let me know, and leave a comment, and I'll be happy to address those questions.